Hello physics, welcome to another flipped lecture, jumping into chapter 20, electrical flow and resistance. And we're talking here about electrons that are moving through a circuit and things that slow them down. So we're going to be talking about the analogy of water moving through pipes. And this chapter is not about water, but if that analogy helps you, it helped me figure this out as I was trying to figure it out, then hopefully that is useful to you. Okay, here we go. We looked at charges that were stationary, static charges, and now we're looking at charges that move. And they move because they are repelled or attracted by other charges. And when charges move, they do so because of pushes and pulls with other charges. They don't just move because they feel like it. They do it because they are shoved there or pulled there by another source of charge. And when electrons move, we call that electrical current. And we use the letter I to represent electrical current. And I don't know why, probably a Latin word. Those of you who remember Latin should fill me in sometime. But we use the letter I to represent current. A current is made up of free-flowing electrons in a metal. Now, it doesn't always have to be a metal. There are some other strange materials that can conduct electrons in particular situations, but 99.99% of the time when electrons are moving, they're doing so through a metal. And if you remember from chemistry, metals are cool because they hold their electrons very loosely. And it's that loosely held electron that allows for electrical current to flow through a wire, through a metal object. Okay? Current is measured in amps. So if you think of electrons moving as water going down a river, we're going to do this analogy a bunch today. An ammeter, a meter that measures amps and current, would be like a water wheel that you put in the river, and as the water goes by, it's turning and it's able to tell you how much water has passed that point. So amps is the amount of electrons moving past any point in the circuit per unit time, number of electrons per second. And so in our analogy that we're going to use a bunch, water moving by, you could put like a little water wheel in, and as it spun, it would tell you how much water has passed that point. Okay, that's an amp, and it's spelled French, ampere, and so, but we in America say amps because we don't like saying ampere, but that's the word, and that's why it doesn't look like amp to you, because that's the American butchering version of the word. We use a capital A as the unit of measurement, so don't confuse I and A. I is, like, in theory, the concept of current. A is the unit of measurement of a current. Wish it were the same letter. Sorry, it's not. They don't ask me about these things. Here is a picture. Again, electrons moving down a wire is kind of like water going through a pipe. And an ammeter, an amp meter, would be measuring the number of electrons passing by this wire at any given moment, right? How many electrons are there going through, like putting a water wheel at the end. Electricity and water have a lot of similarities in this analogy. Electrical potential is the charge at a given location. And this we've already dealt with, right? We already know about volts. Volts are not new to us, but we're going to talk about them again here. So the electrical potential at any given point we would measure in coulombs, but then the charge separation between 2 points we measure in volts. So when you say that a battery is a 1.5 volt battery, you're not talking about the number of coulombs of charge on one electrode. You're talking about the difference in charge between the two electrodes. A voltage is a charge separation, a difference, a subtraction problem, right? And the answer is in volts. What's the charge difference from point A to point B? We measure that in volts, okay? So 1 volt is a joule of potential energy per coulomb of charge. A volt is a J over a C. And so we use a volt as the measurement of charge separation. When we are looking at a circuit, most of the time electrons flowing through a circuit are going to be provided to us by a battery. A battery is a device that provides a steady flow of electrons. Generally, a battery is a kind of something called a voltaic cell. A voltaic cell is a larger category of device that produces a steady flow of electrons. A voltaic cell can be composed of lots of things, kind of a gross little story in physics and chemistry. The first voltaic cell was made out of dead preserved frogs. Yeah. They had some dead frogs that they had soaked in alcohol, and the alcohol provided the electrolytes, and the body fluids of the frog provided the electrolytes. And they had two different kinds of metal pins that they were using to dissect the frog. And when the two dissimilar pins punctured the frog, there was a charge created, and the guy doing the dissection got a shock. And he was like, "What is that?" And that started the study of what caused that shock. And dead frogs and dissimilar metal pins turned into batteries. Yes, folks. So next time you see a dead frog, thank him for your Duracells. And when electrons flow through a conductor, we call that a current. And there's always a little bit of resistance to flow. Back to water. Water going down a river does not flow unimpeded. There's rocks in the river. There's fallen logs in the river. There are narrow points of the river that make the water back up a little bit. And all of those things cause resistance to flow, right? If you're talking about a pipe and water flowing through a pipe, then as the pipe gets smaller, there's some resistance to flow. And even if it's a nice big pipe, the water molecules are stuck to the edge of the pipe a little bit and slow down the flow right on the edge. So water flow is a good analogy here again. It doesn't flow unimpeded. It slows down a little bit as it flows. And that resistance, in electrical terms, is called resistance. Yes, and that's helpful. And we measure resistance in a unit called an ohm. Ohm. We're not meditating. We don't do that. We're a Christian school. But that's the unit of measurement, is the ohm, and it's represented by the Greek letter omega. And it's not called an ohm because we use omega. I think we use omega because it sounds like ohm. It's named after a dude who came up with this, right? There was a Mr. Ohm at one point. And devices which provide resistance are called resistors, and the resistance is usually made by a device that gives off heat. So it's going to take electrical energy, and it's going to slow down the electrical energy and bleed some of that energy out of it, and it's going to turn that into heat, and the resistors get a little bit warm, and that bleeds off some of the energy and slows down the flow of the electrons. Why do you want to slow down the flow of electrons? For all kinds of reasons, but the device that does that called a resistor. So again, if water is flowing through a pipe and you squeeze the pipe, then it's going to be providing resistance. And the unit of measurement for that is the ohm. This is a Mr. Ohm, slowing down the flow, right? And then you could measure a voltage difference across the two. You could say, hey, look, at the battery, there's a certain potential. And there is a different potential here because we've bled out some electricity by the resistance. So you'd get a voltage difference there. All right? Now, water pressure on one side of a valve would be like the voltage over here. Voltage is like water pressure, making the water want to move. And then a valve is like a resistor, and it slows down the flow. There's less flow here. There's fewer amps moving through this wire per unit second, okay? And there's less voltage, there's less pressure. So less voltage after the resistor, more voltage before the resistor, and the water flowing through would slow down here, okay? Ohm's law. This is why we measure resistance in ohm units, because this dude, Mr. Ohm, came up with this relationship between voltage, current, and resistance. And this little triangle is very handy, and it's not in your book. I highly suggest you pause and write this somewhere in your book or in your notes and know where to get to it quickly. VIR in a little triangle. really handy. If you are looking for voltage, then you multiply current times resistance, and that will give you the voltage at any one point. If you're looking for current, you divide voltage by resistance. Volts divided by ohms is amps. If you're looking for resistance, divide volts by current. Volts by amps gives you ohms. So Ohm's law, your book just gives it to you this way and then says, hey, look, you can rearrange it. But this little triangle does the rearranging for you. Cover up whichever one you are looking for and read across what's left. Multiplication, division, division. That's really handy. So Ohm's law in this little triangle. Okay, let's do some Ohm's law because that sounds like fun. I'm going to move my beautiful picture down here. Okay, what is the voltage drop across a 3 ohm resistor in a 5 amp circuit? Now, first of all, that's a stupidly large resistor. Most of the time resistors are not more than 1 ohm. Most of the time resistors are fractions of an ohm. But for the sake of this example, we'll pretend that this resistor is a 3 ohm resistor. Okay? Pretending. That's not what that is. Pretending. But we have 5 amps, we have 3 ohms. Look at my little Ohm's law, cover up voltage, because that's what I want to find out. That's left, it leaves me a multiplication problem. Current times resistor, current times resistance, current times resistance, 5 amps, that's my current, times my 3 ohms, 15 volts. If I had a 3 ohm resistor, and if there were 5 amps of current flowing through it, then I could put a voltmeter here and find that across this resistor there's a 15 volt change. Okay? That's how that works. Last little bit of knowledge, and I'll move my picture again, because why not? Joules law. The last one was Ohm's law. This is Joules law for electrical power. So this is what the power company wants to bill you for. They don't bill you per electron. They don't bill you per volt. They don't bill you per amp, because those things are hard to measure. But they can bill you for how much work you do with the electricity that they provide you. So they do. And they bill you based on watts, right? And not just 1 watt, because that's a small thing. They bill you on thousands of watts at a time. And they bill you on kilowatts used and the time that you're using them. Kilowatt hours is how your electrical bills are written. But we're going to show you what a watt is, right? Power is the amount of work that you do per unit time. And so if it were generally power, we'd be talking about work per unit time. In electricity, we have a particular formula for it. Here we have power, and this is measured in watts. Okay? Is current squared, amps squared times the resistance. Amps squared times the resistance. This looks very much like Ohm's law, right? V equals IR. Here, P equals I squared R. Similar, don't get them confused. If you memorize the triangle for Ohm's law, then that will be helpful for you, because Joule's law is not a triangle. Okay? So, current measured in amps, resistance measured in ohms, power measured in watts. P equals I squared R. Let's do a little bit of math. How many amps does a 60 watt light bulb, 60 exactly, watt light bulb draw in a circuit if it provides 500 ohms of resistance? Wow, that's a crap ton of resistance, but that's okay. We'll pretend that that's right. So 60 watt light bulb, 500 ohms of resistance. What's the amp draw? P equals I squared R. 60 watts, I squared, that's what I'm looking for. How many amps? Oh, look, see, I said 0.500 ohms. That's better. The period got messed up. My bad. 0.500 ohms. Makes much more sense. So let's solve for I squared, right? So we're going to divide both sides by 0.5. That turns this into 120 equals I squared. So let's square root both sides. Square root of I squared is I, square root of 120. I equals then 10.954 amps. I have 2 significant digits and 3 significant digits. I need 2 two significant digits in my answer, 11 amps. Alrighty, so that's how many amps a half ohm resistor in a 60-watt light bulb would consume. Alrighty, this is also not in your book, but you should write this down. This is the unit conversion from anything to anything in electricity. Watts, volts, current, amps, and ohms in resistance. If you want to know how do I convert from volts and amps to watts? Well, volts and amps to watts. How about volts and resistance to watts? Here's volts and resistance to watts. How about amps and resistance to watts? Here's amps and resistance to watts. This will convert from any other unit to the one you're looking for, and this shows you the math equation for it. Don't memorize this. Write it down somewhere, have it as an easy reference. And then anytime you're doing electrical circuits and you need to know how do I get from the 2 units I have to some other unit, this little magical wheel will help you with that. Alrighty? God bless you. If you have any questions, I'll see you tomorrow. Have a wonderful evening.